We had left off in 1923 when, as Einstein remarked, the bride had lifted a corner of the Great Veil. By that time, it was already clear that light, and waves in general, exhibited a dual particle wave nature. In some experiments, they behaved as waves, governed by Maxwell's equations, while in others they behaved as particles, following Newton's laws of dynamics. What the bride proposed in his 1923 doctoral thesis was that just as waves possess a dual particle wave nature, the same could be true for particles. Therefore, what we have always thought of as particles can also be thought of as waves. The bride derived the wavelength associated with a particle of mass m and velocity v, which is equal to h over m times v. Given the extremely small value of Planck's constant, it's evident from the formula that this concept holds significance only at the microscopic level. For typical mass and velocity values in the macroscopic world, the wavelength is practically zero. To support his hypothesis, the bride went as far as to predict that if we were to repeat Young's famous experiment, shooting a beam of electrons at the two slits instead of light, what we would observe on the screen would not be the two bands we'd expect if electrons were particles, but rather an interference pattern, just like waves. Just as with waves, the phenomenon of interference would only be observed if the slit width matched the wavelength of the incident wave. However, the wavelength of an electron, as given by his formula above, is extremely small, and at that time, the technology needed to achieve such precision was unavailable. But only 3 years later, the Americans Davison and Germer were able to conduct the experiment hypothesized by de Broglie by bombarding a nickel crystal with a high-energy electron beam. And what do you think they found? They found an interference pattern, just like waves. Totally insane. De Broglie was right. But let's pause for a moment and carefully analyze this experiment in detail. Not only because it is universally regarded as the most beautiful experiment in the history of physics, but also because, as the great quantum physicist Richard Feynman later remarked, it contains and represents the heart of quantum mechanics. Its interpretation is one of the best ways to illustrate the fundamental principles of quantum mechanics. It's clear, intuitive, and experimentally verifiable that if we shoot particles, such as tennis balls, at the two slits, those passing through the left slit will land in the left band, and those passing through the right slit in the right band. However, if it's a wave directed towards the slits, the two slits become two wave sources, and the waves generated by the two slits interfere with each other, both destructively and constructively. This creates the well-known interference pattern, where bright bands indicate points of maximum intensity, constructive interference, and dark bands correspond to minima, or points of zero intensity, destructive interference. This was precisely the result obtained by Young in 1801 using a beam of light, which established the wave-like nature of light beyond any doubt, or so it believed. Then, in 1927, Davison and Germer managed to replicate the experiment using a beam of electrons and two slits of a width comparable to the electron wavelength given by de Broglie's formula. They expected a two-spot pattern typical of particles, but instead observed an interference pattern, characteristic of a wave. De Broglie's idea wasn't so far-fetched after all. At first, one might think that the stripe pattern could be due to interactions between the electrons, since electrons are not just simple particles. They carry a negative charge and could repel each other, influencing their trajectories and somehow producing the observed pattern. However, even when the electron flow is reduced to the point of sending them one at a time, so that no more than a single electron passes through the slit at any moment and interactions between particles are impossible, the result remains unchanged. After some time, the detector will once again show an interference pattern. But the surprises don't end here. Although we don't understand why an interference pattern forms rather than the expected two-spot pattern, we might at least expect that the left bands are caused by electrons passing through the left slit, and the right bands by electrons passing through the right slit. There should be no surprises in this regard. So, let's block one slit and check this out. But what was discovered was even more astonishing. With only one slit open, the electrons spread almost uniformly across the screen. This is mind-blowing. An electron must either go through the left slit or the right slit, So the pattern with both slits open should be the sum of the two patterns from having only one slit open at a time. But it's not. Not only that, but with only one slit open, the electron can land in any position, whereas with both slits open, there are regions where it never lands. Now, if the electron passes through the right slit, nothing should change whether the left slit is open or closed. Yet, it seems that the electron is somehow influenced by the condition of the adjacent slit. If it's also open, it behaves one way. If it's closed, it behaves another. One might be tempted to think that the electrons are intelligent, aware of whether both slits are open or not, and adjust their behavior accordingly. Or, perhaps even more absurdly, that when both slits are open, the electron somehow passes through both slits simultaneously, resulting in a different behavior when we close one slit. At this point, before going mad, I decide to leave both slits open and place detectors that tell me which slit the electron passes through, and solve the mystery. But instead, if anything, the mystery deepens even further. When I use a passage detector, the electrons distribute themselves uniformly across the screen, behaving exactly as expected, as the sum of the results obtained by closing each slit alternately. So, not only does the electron seem to know whether both slits are open, but it also seems to know when we are watching it. And, almost like a person, it behaves differently when being observed. So, are electrons thinking beings? Let's try to stay sane and recap by establishing some solid points. First of all, we must admit that de Broglie was not a madman. The fact that the electron produces an interference pattern tells us he was right. Particles also possess a dual nature, and in this case, they behave like waves. Now, if particles truly have a wave-like nature, they should be governed by a wave equation that describes their behavior, much like in classical physics, where Newton's second law, F equals ma, describes the behavior of a particle. However, after presenting his revolutionary idea, de Broglie was not quick enough to develop a rigorous mathematical theory, and he was overtaken by the Austrian physicist Erwin Schrödinger. In 1926, just a year after de Broglie's thesis, Schrödinger achieved this by constructing his famous wave equation, now known as the Schrödinger equation. He actually wrote his equation during Christmas of 1926 in a chalet in the Swiss Alps, where he was vacationing with his lover. It was well known that besides physics, Schrödinger's other great passion were women, to whom he credited his creative inspiration. In the photo, we can see Schrödinger's wave equation engraved on his tombstone. Here, H is the Hamiltonian operator, a mathematical operator representing the particle's total energy, kinetic energy plus potential energy. Notably, the presence of the imaginary unit in the equation prompts us to reflect on how what might seem like a purely abstract mathematical concept appears in an equation that describes reality. Creepy, right? Electrons, therefore, are nothing more than waves, more precisely wave packets, whose behavior is perfectly described by a wave function that is a solution to the Schrödinger equation. But if that's the case, how do we explain the particle-like behavior of the wave? For example, in the double-slit experiment, when the electron is detected on the screen, it appears as a particle in a specific position. According to Schrödinger, what happens is that when we observe and detect the particle, the wave function collapses. That is, its energy instantaneously concentrates at a single point. In other words, it becomes a wave so small that it appears as a particle. Schrödinger's mathematical theory became known as wave mechanics, and it is in perfect agreement with experimental results. It represents the first of three major interpretations of quantum mechanics. Legend has it that in developing this theory, Schrödinger sought assistance from the mathematician Hermann Weyl, who initially refused due to his busy schedule. Schrödinger then reportedly offered Weyl his wife's company in exchange for his help, and thus, thanks to Anne-Marie's sacrifice, wave mechanics was born. According to this interpretation, there is no wave-particle duality, only waves whose behavior is perfectly described by Schrödinger's equation. The particle-like behavior is explained by the collapse of the wave function. It doesn't make sense to speak of the electron's position. As a wave, the concept of position doesn't apply. Instead, it has energy distributed across space according to the wave function. Only at the moment of observation does the wave collapse to a point, assuming a definite position. If we really must answer the question, where is the electron, the response would be, a bit everywhere, just like my voice, a sound wave, which is present all around this room. Indeed, you can hear me no matter where you are in this lecture hall. The double-slit experiment is perfectly explained by this interpretation, as shown in this splendid video from the French website Tout est Quantique. With both slits open, the electron behaves like a wave that simultaneously passes through both slits, interferes with itself, and creates the phenomenon of interference. When it reaches the screen, the electron is detected, and its wave function collapses to a point, which is what we observe on the screen. The electron can only collapse where the wave is present, hence the observed interference pattern. This is exactly the behavior we would expect from a wave, such as light or a water wave, which we can see in this second video. So, if we ask through which slit the electron passed, the answer is both. After all, it's a wave. What's so strange about that? If we leave only one slit open, the electron passes through the open slit, which then acts as a wave source, generating a single slit diffraction pattern, not an interference pattern, resulting in a broad, uniform distribution of points on the screen. When we place a detector on the slit to determine which one the electron passes through, observation modifies the experiment. The presence of the detector forces the electron wave to choose one slit to pass through, collapsing at that point and manifesting itself. Once it passes the detector, it resumes wave behavior, bringing us back to the previous case. Thus, the resulting pattern is correctly the sum of the patterns obtained with only one of the two slits open. So, everything is clear, or maybe not quite. Two unclear points remained in Schrödinger's theory. First of all, what exactly are these waves? What is it that vibrates in them? In ocean waves, it's the water that vibrates. In sound waves, it's the air. But in these matter waves, what is it that vibrates? Secondly, regarding the collapse of the wave function, an instantaneous collapse implied an infinite speed, therefore greater than the speed of light. This conflicted with Einstein's theory of special relativity. From that point on, Einstein, despite acknowledging the numerous experiments confirming it, became the greatest critic of quantum mechanics. Quite the coincidence. A solution to these problems was proposed by the German physicist Max Born. According to Born, Schrödinger's wave equation doesn't describe a real, tangible object, but serves as a mathematical tool to describe reality. Specifically, the square of the modulus of the wave function represents the probability density of the particle's presence at a given time and space. So, for Born, the particle is not an actual wave that collapses. It remains a particle. It's just that its position is described in probabilistic terms, rather than as a definite and localized quantity. This is as counterintuitive as one can imagine. No wonder the great physicist Richard Feynman would later say, "I think I can safely say that nobody understands quantum mechanics." As physicists often say to themselves, when a new theory arises, it's not that we understand it, we just get used to it. To help clarify this concept, we can refer to the following example from our everyday life. Macroscopic world. Imagine a typical mathematical high school student spending an afternoon in his room. Until we enter, we can only guess what he might be doing. Knowing students from the mathematical high school, we could reasonably say that there's a 30% chance he's taking a nap on a bed, a 10% chance he's studying at his desk, a 20% chance he's lying on the floor scrolling through TikTok, and a 40% chance he's at his gaming setup challenging friends online on the PlayStation. When we open the door and observe him, we'll find out what he's actually doing. probably playing PlayStation. Microscopic world. Now, let's imagine that an electron is in the room. It too can be in various positions, but unlike our knowledge of the student's habits, the probability of each position is given by the square of the modulus of the wave function, which is a solution to Schrödinger's equation, and describes the electron's behavior inside the room. So, it might be in one spot with a certain probability, in another with a different probability, and so on. When we observe it, we'll find it in a single location, just as we would with the student. The fundamental difference between the macroscopic and microscopic worlds is that for the student, we can say that before observing him, he is either on the bed or at the desk or on the floor or somewhere else with certain probabilities. But the electron is, with various probabilities, in all of these positions simultaneously. As they say, you get used to it. You don't really understand it. For the double-slit experiment, the explanation is exactly the same, except that now the wave function is not a real, tangible object, but a mathematical tool to determine the probability of finding the particle at a certain point at a certain moment. We now fully understand the interference pattern, the central band with the highest density of collision points, and the lateral bands with decreasing collision density. This is a mathematical consequence of the fact that the central band is where the intensity of the wave function, and thus the square of its modulus, representing the probability of finding the electron, is highest due to constructive interference. The German physicist Werner Heisenberg suffered from hay fever. For him, spring was not a pleasant season. Instead of staying in Copenhagen, where he worked at the Theoretical Physics Center established by his mentor Niels Bohr, he decided to go to the island of Helgoland, a small, nearly plantless rock of about 1 square kilometer, and thus pollen-free. There, in solitude, in June 1925, he discovered a procedure that allowed him to obtain all experimental data. It was an unusual procedure that involved multiplying a table of values by a row of data. Heisenberg had invented it entirely on his own. Heisenberg's guiding idea was that one shouldn't worry about the nature of things, but only about the outcomes of experiments. It didn't matter whether an electron was a particle or a wave while it propagated. What mattered was the ability to predict measurement results. Heisenberg represented quantum observables such as position, momentum, energy, etc. with these strange tables that encoded information about possible measurement outcomes and the likelihood of observing specific values. Using them, he was able to brilliantly predict experimental results. Heisenberg was 24 years old, and for that hay fever, he would receive the Nobel Prize in 1932, just 7 years later. Following Heisenberg's preliminary work, Max Born and Pascal Jordan helped formalize the mathematical idea into a complete and coherent structure, leading to matrix mechanics in its final form in 1926. The first thing Max Born, yes, him again, pointed out to Heisenberg was that these strange tables were none other than matrices, a concept well known to mathematicians, but less familiar to physicists at that time. The following year, Schrödinger himself proved that the two theories were equivalent and led to the same results. The only difference lay in the mathematical form used. Schrödinger's theory gained more popularity among physicists since it employed mathematics that was more familiar to them. But the best was yet to come. This time, it wasn't hay fever that helped Heisenberg. After all, it was winter. It was the solitude after a period of intense discussions with Bohr and even Schrödinger, who was visiting Copenhagen. Bohr had just taken a vacation to Norway, and Schrödinger had left for the United States to give a series of lectures. At that time, Heisenberg lived in the attic of Bohr's institute. The breakthrough came one night after a walk in the nearby park. Suppose, for example, we want to know the position and momentum of a particle. Let's denote the uncertainty in the position measurement as delta x, and the uncertainty in momentum as delta p. Heisenberg demonstrated that no matter how precise our measuring instruments are, there is a fundamental limit to the accuracy with which we can know both position and momentum simultaneously. In formula, delta x times delta p needs to be bigger or equal to h over 4 times pi. So, the more accurately you know the position, that is, the smaller delta x is, the less accurately you know the momentum, that is, the larger delta p is, and vice versa. It's important to understand that reality itself is indeterminate. It's not that we, as observers, are simply unable to precisely see both the position and velocity of a particle at the same time. Rather, it's the particle, and thus reality itself, that is inherently like this. As Heraclitus observed centuries earlier, nature loves to hide. This also applies to other pairs of observables, physical quantities, such as energy and time. But Heisenberg hadn't reckoned with his boss and mentor, Niels Bohr. Returning from his vacation in Norway, the two began increasingly animated discussions about the nature of the uncertainty principle. In March 1927, Bohr observed that Heisenberg's uncertainty principle was simply the mathematical manifestation of wave-particle duality. Let's consider a monochromatic wave, that is, a wave composed of a single frequency, with wavelength lambda. This wave has a well-defined momentum, given by h over lambda, but its position is entirely indefinite. In fact, a monochromatic wave is spread out. It occupies, so to speak, all of space. On the opposite end, let's consider a wave packet. A wave packet is the sum of many waves of different frequencies, combined so that constructive interference occurs only within a small region of space. Outside this region, the sum quickly drops to zero. The length of the wave packet decreases as more different frequencies are combined. Thus, the localization of the wave packet becomes more precise as the range of frequencies increases, making momentum more indeterminate. In the limit, with an infinite range of frequencies, completely indeterminate momentum, we achieve precise localization at a single point, which Schrödinger referred to as the collapse of the wave. This reflection led Bohr to formulate the famous principle of complementarity, which constitutes the third interpretation of quantum mechanics, known as the Copenhagen interpretation, named after the city where Bohr's Physics Institute was located, where he and Heisenberg worked. It makes no sense to ask whether quantum objects, like electrons and photons, are waves or particles. Electrons, photons, and so on are both particles and waves, both simultaneously. They are two sides of the same coin, and just as with a coin, we cannot observe both sides at once. When we observe one side, we must forgo looking at the other. As long as the coin is spinning, both heads and tails are present. But the moment we stop it with a slap, we observe it, it reveals itself as either heads or tails. This is perfectly summarized by the phrase contraria sunt complementa. Opposites are complementary. They are the same thing, which Bohr included in the emblem of his Copenhagen Institute of Physics, alongside the Chinese symbol of Tai Chi. Bohr presented his interpretation in 1927 at one of the famous Solvay conferences, scientific meetings held in Brussels and founded by industrialist Ernest Solvay. Yes, the same one associated with baking soda. At this conference were all the most prominent physicists, including all the figures we've encountered on our journey, starting with the father, Max Planck. Despite its profound illogicality and lack of intuitive understanding, this theory has become the most widely accepted interpretation to this day. Why? Because it works. Schrödinger, who was also present at the Solvay conference, couldn't stand it. Wave mechanics worked so well. What was this idea of the principle of complementarity all about? To highlight the absurdity of Bohr's theory, Schrödinger invented the famous Schrödinger's cat paradox, which earned him praise from Einstein. another historic opponent of the principle of complementarity. Einstein's well-known remark about this was, "God does not play dice." Imagine locking a cat in a box. Inside the box, there's a piece of radioactive material. Suppose that every hour, the material has a 50% chance of decaying. If it decays, a detector registers it and triggers the release of a vial of deadly poison, ending the cat's life. According to quantum mechanics, there's a 50% probability that the event occurs, resulting in a dead cat, and a 50% probability that it doesn't, leaving the cat alive. Now, if we accept the principle of complementarity, then as long as we don't open the box, the cat is both alive and dead simultaneously. Only by opening the box and observing will we find out whether it is alive or dead. Hence, the fate of the unfortunate cat is in our hands. It's our observation that determines the outcome. Meanwhile, the cat finds itself in a strange limbo, neither fully alive nor fully dead, a paradoxical state dictated by the peculiar rules of quantum mechanics. This superposition, the cat being both alive and dead until observed, highlights the unintuitive nature of quantum theory, leaving the poor creature's fate hanging in uncertainty. In Schrödinger's mind, this absurd scenario was meant to illustrate the strangeness of Bohr's interpretation. But, ironically, the thought experiment has since become a cornerstone for understanding quantum mechanics, symbolizing the mystery and complexity of observation and reality at the quantum level. Quantum mechanics still had a problem when the speeds involved approached the speed of light, and this implied that Einstein's theory of relativity had to be considered. In 1929, this problem was solved by Paul Dirac with his relativistic wave equation. The solution of this equation gave a perfect description of the motion of quantum objects at speeds close to that of light. With the publication of the book The Principles of Quantum Mechanics, the quantum theory took the final shape with which we are now familiar. Very little theoretical progress was made in the decades that followed these breathtaking developments. On the other hand, these later years have been quite fruitful in the field of experimental studies, especially in the investigation of the numerous newly discovered elementary particles, like anti-electrons, anti-neurons, anti-protons, etc. In conclusion, quantum mechanics is completely counterintuitive and difficult to comprehend and accept. Not surprisingly, as previously mentioned, the great physicist Richard Feynman would later say, "I think I can safely say that nobody understands quantum mechanics. But it has one great merit: it works." And, as already said, physicists often say, when a new working theory arises, it's not that we understand it, we just get used to it. Therefore, even in everyday life, if something works, use it, do it, without worrying too much about why.